Uh, Great. Okay. Cool. Um, just that. Okay. Hi everyone. I'm Ethan. We're not expecting anyone else, right? Or are we expecting, or just people will trickle in? Okay.
More impact.
Yeah. No worries. No worries. Okay. Yeah. Okay. So today I'm going to be talking about this work that was at Eurocrypt this year, called "Black Box Crypto is Useless for Doubly Efficient Private Information Retrieval." This is joint work with Wei-Kai Lin at Virginia and my advisor Daniel Wicks. Oh, why did that? There we go. Okay, so oh yeah, and also feel free to interrupt at any point. These are I didn't really have time to update my slides since my Eurocrypt presentation, so this will be a little bit short on the slides, and hopefully it won't be too rough. And then we'll transition, maybe do a little bit on the board, depending on time. But okay, so. Let's start with just a brief description of what is private information retrieval and what are we doing here. For the purposes of this talk, I want you to think about private information retrieval as being some sort of protocol between a server and a client. And it is a protocol where a server holds some public database, and it wants to make that database available to the client, or perhaps many clients, but let's just say the client for now. And the client wants to just access some location in the database, right? And so they engage in some protocol, and at the end, the client recovers the ith index, or like the ith location from the database. And what we want is that out of this protocol, that the server learns nothing about the location that the client was asking for, right? So like it's indistinguishable whether the client was querying on I or I prime for any two arbitrary I and I prime. And crucially, like there's, you might think like, okay, there's like a trivial solution to this. If I get rid of this requirement that I showed, there's a trivial solution, which is the server just sends the entire database along to the client on the wire, right? And so this is like a very, very unsatisfying solution, because like I don't want to have to download, perhaps tons and tons of data when all I'm looking for is like kind of one location. And so what we'll require, for the purpose of this talk, all we're going to say is that private information retrieval becomes interesting as soon as you're in sublinear land, anything sublinear. Ideally, and what we can actually achieve in just the general sense, is you kind of want polylogarithmic, like something that is approximates the amount of data that the client would have to download if it was just asking the question in the clear, right? And so, however, there is like one kind of glaring lower bound that comes with standard private information retrieval, and that kind of inherently the server must touch every single location in the database in order to respond to the client's query. And as a result, the server's runtime is at least linear in the database size. And just to see, like, kind of very briefly why this lower bound is the case, is like, okay, imagine the server was able to answer the client's query and just touch every location except for one. Then, by the fact that the server answered the client's query, but the fact that it didn't touch this location, it kind of tells you that the server did not just give the client the data at location I, or that location it didn't touch. And so you sacrifice some amount of security. It's like the server doesn't touch every single location. And for those just filing in, we're briefly recapping the definition of private information retrieval. And we just saw this kind of really simple motivating lower bound behind this kind of whole idea of doubly efficient private information retrieval. Anyone who just came in?
This works for computational schemes as well.
Yeah. This is a super general lower bound. Just like if the server only stores the database and nothing else, if I don't touch location J, I obviously didn't give you location J. It doesn't matter anything about the efficiency. Okay, so So that lower bound is kind of the motivation why we asked the question about studying what we'll call doubly efficient private information retrieval. And I use this term doubly efficient to mean that like, whereas private information retrieval you can kind of think of as being that kind of sublinearity requirement is like a client efficiency thing. And that like the communication that the client has to endure, and ideally the computation of the client as well should be the kind of sublinear in the database. In addition to that, we want that the server's runtime is sublinear in the database. Like that's like the second of the double. And so the definition of doubly efficient private information retrieval kind of introduces, in addition to this like online phase where we have this communication where the client makes its query, there's an additional offline phase that happens before, and it'll happen just one time, where first there's some key generation that happens, and then using the key that is sampled, and notice I will draw your attention the fact that the key is independent of the database and it's just like sampled one time up front. And then using that key, the database is pre-processed into some data structure that happens again just one time. And then the server, instead of holding just the database, holds this pre-processed data structure, which I'm going to require is like the pre-processing is doesn't blow it up too much. It's just I'm fine with arbitrary polynomial, but it doesn't blow it up like exponentially. And now I kind of want the same two requirements as before, but I want the additional requirement that the server can answer a query by touching only sublinear locations. Okay. And for the purposes of this talk, these are kind of the only requirements I'm going to care about when it comes to doubly efficient private information retrieval. As maybe alluded to by the title of this talk, this is a work about lower bounds. And so I kind of want to give you like the weakest possible version of this primitive and rule stuff out about that. In terms of positive results, we can make this sublinear and this like these things, instead of just sublinear, we can make them polylogarithmic. This polynomial in terms of positive results can be n to the 1 plus epsilon. And I'll say a little bit more about what these keys and stuff like this are in a minute. But yeah, so this is the general framework of doubly efficient private information retrieval.
Okay, and the server do compute the location of it, like after it accesses these locations?
Yeah, certainly. The server can do arbitrary, like whatever computation you want.
So like touching little and locations, does it imply sufficient?
Again, yes. So again, from a lower bound perspective, all we are going to care about is that you'd only touch sublinear locations. From a positive result standpoint, we do want lower computation time, right? And so for the known upper bounds that we have, we do achieve low computation time. But for the purpose of this lower bound, all we care about is the locality. We don't actually care about server computation at all. And indeed, like for the purpose of our lower bound, we also don't even care about client computation at all. Like the client can run in linear time, or even exponential time. I don't care. All I care about is communication and locality on the server side, or lower bounds.
Doubly efficiency is for like this here, efficiency rather than caring about clients.
Yeah. In real life, when if we want to implement this, we kind of care about both of these two parties' computation time, right? But for the purpose of these lower bounds, I'm only going to care about this is an analog of client efficiency, and this is an analog of server efficiency in this kind of lower bound sense. More general, like weaker sense. Okay, so there are three kind of general flavors of PIR that I want to talk about, or like at least kind of familiarize you guys with, that have been kind of discussed at different points in the literature. And so they kind of have these increasing notions of like kind of what's going on in terms of the key material. And so the first one you kind of think of as this key generation generates a secret key, and then that secret key is used to preprocess the database. And like kind of what you should think about in your head is like, here I generate a secret key, and then the client itself does the preprocessing of the database and then hands that database off to the server, right? Alternatively, you can ask like, okay, well, what if I make it so that the schema is still I want to ask that the schema is still secure even if I give away the client key. So the key is now like a public key, and so you can make queries using this public key. And here, like, it's a bit more natural to think of like there's some trusted third party in the sky that does the pre-processing of the database, distributes a public key to all, like, potentially many clients, not just one client, right? And then hands the pre-processed database off to the server. And finally, there's this kind of notion of unkeyed DPIR, where here the pre-processing doesn't depend on the key at all. And it's just some deterministic process that the server can do by itself. Okay? Yeah.
So the difference between secret key and public key is the key is known to the client in the secret key setting, but not the server.
Yes, in the secret key setting, the key is known to the client, but not the server. And like thus the honest party, but not the adversary, right? Here, the adversary gets to see the public key as well. And so security holds against a stronger adversary.
Oh.
Yeah. And so,
sorry.
yeah.
The unkeyed setting, is it important that the prep method be deterministic? Can it not be randomized?
It is not important necessarily. I mean, okay. It's more natural to think of it this way because kind of there's like, I mean, like it could very well be randomized. Like this is like a little bit like more natural of a concept just because it's like, oh, the server just kind of can do this like one-time thing and it's just kind of some specific process. You kind of get some canonical representation of the database. And it turns out like the positive result does have this. But you could consider the other version. Yeah.
So for the secret key setting, why not just use ORAN?
Yeah, so that's a very good question. And kind of the answer is, in terms of practical applications, I don't have an answer for you. I'm pretty much always happy to use ORAM instead of secret key DPIR. I don't really have any theoretical applications and specifically. So and that's kind of why like this is a bit less like people don't necessarily haven't studied this specific primitive as much in terms of like positive results for it because it's kind of not super useful. There's this recent paper by Yuval and I'm forgetting the co-authors. Yeah, which does build like some secret key DPIR from some LPN type assumptions. And I mean, it's a very weak form of DPIR. Like,
what's the overlap? Is it like all around like polylog or is it much worse?
It's much worse. It's actually well, okay, so it's polylog communication, but much worse server runtime. The server runtime is like n over log n. Like it's barely doubly efficient.
So what's the point of their paper in comparison with your result?
So their paper kind of is less focused on the DPIR aspect and more focused on just the question of. Actually, okay. Let me finish the slide and then come back to this question. Okay, so yeah, so okay, so in terms of prior constructions, what we have, there are these two works by Canetti, Holmgren, and Richardson, and Boyle-Ashai, Pass, and Wooters in 2017, that both using very similar constructions, both constructed these kind of first constructions of secret key DPIR. But they were both from this kind of non-standard assumption about like kind of permuted codes with noise sort of thing. And also observed in those papers is that one can actually upgrade secret key DPIR to public key DPIR if you allow yourself like this super heavy hammer of heuristically using obfuscation. In kind of the natural way that you would expect of like upgrading secret key to public key things using obfuscation, if you're familiar. And then more recently, myself and the same two authors constructed unkeyed DPIR, like this kind of stronger notion based on the ring LWE assumption a few years ago. And it's not too hard to see, like for instance, that you have like implications this way, like this is the strongest version of this is the weakest version. But one thing that I want to point out is that like only unkeyed DPIR itself actually implies normal PIR, right? Normal PIR is this kind of is a public key primitive, like it itself implies oblivious transfer and a bunch of other public key.
So what is standard PIR? That
Like just the normal notion of PIR, like.
In the law, it's no.
Yeah, no pre-processing. Yeah, exactly.
Are there any implications of standard PR with public key or secret key? Or are there any like arrows from standard PR?
We don't know. Yeah. But the reason I put off answering Elaine's earlier question is this work with Yuval, this recent work, kind of gives like some amount of justification that at least like if you take away the DE parts of all of these things, you can still kind of ask these questions about like the notion of pre-processing PIR. And you could ask about like, well, what if I want to do PIR with weaker assumptions, right? Like standard PIR, kind of, which is analogously like kind of in this unkeyed setting, there's no pre-processing. But standard PIR already implies public key cryptography. If I allow myself some pre-processing in the first place, like with public key or even secret key, these secret key notions, I could potentially ask for PIR with weaker assumptions. And one of the takeaways from Yuval's paper is that they build a secret key pre-processing PIR that's, you can sort of see it as a DPIR because it's like barely doubly efficient. It's like very slightly sublinear, but really very slightly. But really like the idea is that they build a secret key PIR from assumptions that we don't know to imply public key cryptography. Like LPN in a parameter regime that we don't know implies public key. Yeah. But yeah, so I mean, really what I want to like point out is that like secret key PIR kind of in terms of like, I mean, as you kind of pointed out, Elaine, like there's kind of not much so we kind of restrict our focus to this very strong or this very restricted notion where the key is independent of the database and static, right? So this rules out both ORAM and kind of client-side pre-processing PIRs in this notion of secret key PIR, right? But it kind of doesn't, but it's also not super useful. Like I don't necessarily have like strong justifications for why we have those restrictions other than that kind of loosely techniques wise, it kind of more matches up with what we get towards getting all the way to unkeyed, but also, I mean, and then just kind of, it's like a more of a purely theoretical question without even like super strong theoretical implications. Okay. But okay, so I've kind of given you this kind of lay of the land in terms of these three flavors of DPIR. And now what I'm going to talk about is a lower bound result, right? And so I'm asking the question, how do these notions of DPIR relate to other crypto primitives? And so kind of the typical way that we think of relations between crypto primitives, I mean, like the default way is like, like, oh, this primitive, like the standard PIR is unlikely to be implied by one-way functions because PIR itself implies public key cryptography. We don't think public, like, so we kind of have this like large, like we have like a couple of core results saying like one-way functions are unlikely to imply public key cryptography in a black box way. And then we have like this tree of things that imply public key cryptography. And those are the things that are unlikely to be implied by one-way functions, right? But what we get as a result is like we don't actually show that DPIR implies like any of these versions of DPIR implies blah some other crypto primitive. We show something slightly weirder than that. That's like a bit more akin to showing a black box separation, but still slightly weirder than that. Like still a little bit weird compared to that. And again, our focus in this setting is we're going to focus on the weakest one because it is a lower bound result. And so our question is going to be about symmetric key PIR or secret key PIR, and DPIR, and relate that to other crypto primitives. And so what our main result essentially is that black box use of advanced cryptographic objects of like many, many different types turn out to be like completely useless for constructing DPIR. So what do I mean by that? I mean that suppose I have a crypto primitive that satisfies some specific property. I'm not going to tell you yet. I'll tell you later on in this talk. But it's a very large class. It includes like VBV obfuscation, and it includes the generic group model. Like, so things that can be implied by all these like really fancy, powerful tools. So if I have a crypto primitive that in that large class, if I have a black box construction of skdpir from that crypto primitive, then I might as well have just constructed skdpir from one-way functions. So that's the result that we have. And so this is like, at least to me, this is like a priori a very weird sounding result, right? Like it kind of just says like, oh, all of these like really fancy tools that you have, you might as well not use them. And it's like, I'm not really familiar with other results that kind of look like this. But I kind of want to, like, I want to give you a bit of a taste of like, this is not that weird of a statement. So first, kind of after our work was published, there was a follow-up work that kind of showed the same type of results for this other crypto primitive called pseudorandom codes. And so they kind of showed this other work that has a connection like this. But really, like, okay, this theorem is like even more dumb than that. Like, I claim that the same theorem holds if I replace dpir with like symmetric key encryption. Like if I had a construction of symmetric key encryption from some really advanced primitive, then I also have it from one-way functions. Okay, this is a dumb statement, right? Like then I also have it from one-way functions. Like I already had it from one-way functions. But in general, like the meat of the statement is that like I have this symmetric key type primitive, and it kind of and what you can prove about like this, the idea of this theorem is that like these kind of advanced cryptographic objects kind of don't really help in building these sorts of specifically symmetric key type primitives. And we'll see a bit later in this talk kind of what exactly is going on. And so then the interesting statement is like, the interesting fact is that, you know, we don't believe that you can construct symmetric key or secret key dpir just from one-way functions. And we don't have a full proof of that. We have partial progress towards that in this paper. And so what we get is that there's no backbox construction of skdpir from one-way functions where we have these two annoying adjectives. So I gave you the definition in terms of an arbitrary multi-round scheme, and I gave you the definition where the server is allowed to do arbitrary computation on the stuff that it on the locations it reads from the database. And here, what we can rule out is the situation with two round and passive.
This is like, are you saying you are trying to prove that there is no black box construction of skdpir from one-way function?
Yeah.
That's a corollary. So the actual theorem is that there is no black box construction. So separating one-way function from skdpir.
Yeah, but combining these theorems 1 and 2, it's like we separate more than just one-way functions from skdpir. It's like one-way functions, but FHE is also separated from skdpir. Like obfuscation is also separated from skdpir. Like all of these things are kind of separated from skdpir. Yeah.
Could you repeat what the passive server part means?
Yeah. So by passive server, all I mean is that so the server gets instead of the server getting like a query that's just like some arbitrary string, and then it does some computation, and that computation tells it to look at this location, and then it does some more computation, and then it looks at that location, and so on. Instead, the server just gets a set of indices, looks at those indices in the database, sends back those values, and that's all the server does. Like there's no other computation.
And the theorem 2 is true with certain assumptions.
This is true as written.
Wait, what does it mean, partial progress?
Yes.
Is something you have proven, or you?
So theorem 2 is, I consider theorem 2 partial progress towards ruling out skdpir from one-way functions, because this rules out skdpir from one-way functions with the caveat that I require these, like, I don't rule out general skdpir, I just rule out two-round passive server skdpir, right? What I would like ideally is to rule out general skdpir from one-way functions. Yeah. Okay, and so let's okay, and so
Does the SKDPR imply passive server SKDPR?
yes, yeah. Well, let's I'll get to that in 1 second. You know, like I'll like more explicitly answer your question in just a minute. But before I move on real quick, I just want to make a note. Like just kind of to set your expectations for the rest of this talk. Like here, I think is like kind of the conceptually interesting part of our paper. And here is like, this is like a lot of technical work went in here, and it's like kind of nice, but maybe less exciting. So I'm going to focus on like these kind of conceptual message here. And if we have time, we'll get to this. And this is when we would switch to whiteboard if because I don't have slides on this much. But okay. So let's just talk about the techniques towards proving that theorem one. So as our starting point, let's suppose that we have an SKT-PIR in an idealized world. So it's like, so imagine I have some oracle that implements a crypto primitive as a black box, right? And so I have an SKT-PIR that's built in a black box way with respect to that primitive, right? So that's the same thing as an SKT-PIR in an idealized world. And oh, sorry, yeah, that's good. And so kind of the one key thing to note is that there's nothing hidden from the client in the PIR game, right? So the insight that you can make is that, well, the client can just do all the server's work for it, assuming that the server's work is small enough. And so this is like greatly inspired by the techniques of Jesko and Mohammed at a previous Europa paper. And so the idea here is what we're going to do is we're going to compile our SKD-PIR where the server into one where the server doesn't touch the oracle at all. So this is what we're going to do. We're going to essentially turn it from a normal SKD-PIR into a passive server. That's step one. And then step two, we're going to say if this oracle is nice enough, then we'll argue that the client itself can just emulate the oracle itself. Because here the server doesn't touch the oracle at all. So this client can just emulate the oracle by itself, and we get a DPIR that exists relative just to a PRF, or a random function.
So for the first step, can you make sure that it's just to run?
No, I do not. But
because like the cryptography function itself may have some like dependence on the response.
Yeah. So yeah, what will actually happen is here, this transformation, this part can blow up the round complexity, which is part of why our overall result is a bit unsatisfying to me, right? Like we can't actually say, hey, you start with an arbitrary DPIR from P and you get something that we can rule out. Like we can only rule out the 2-round passive server case, but what we end up is like our transformation from P into the to the PRF version kind of blows up the round complexity. And so that's annoying. Yeah.
Sure, this is an interesting question, but I missed it at the beginning. Does round complexity count just the number, like, can you communicate multiple messages in a single?
Yeah. It's just like the number of back and forth
Just the
speaking.
number, right.
Yeah, exactly. Yeah. It's like counting the adaptivity of things. Yeah. Okay. So let's just give a brief overview of how what happens in step one. So here we're going to talk about removing the server's oracle. So here I'm just going to draw a little picture of like what the normal idealized world DPIR looks like, right? So the client can interact with this oracle, send some message, the server gets to interact with the oracle, looks at some locations in the database, potentially could interact with the oracle again, do whatever it wants, sends back a message, and we kind of repeat that process over and over again, right? Okay, so that's what the normal one, and we want to transform it into a kind of passive server version, where all that we're going to do is we're going to define this new client, where the new client is just going to run the client and the server of the original guy. And every time that they would want to access the oracle, this client's going to access the oracle for them. And anytime that the server and this inner server wants to touch a location in the database, the client is just going to send that location over to the real server. Server will look it up and send it back. And so we kind of repeat that process over and over again. And so we've kind of turned the original scheme into one where the server is completely passive and doesn't have to touch the oracle at all. But, and as I mentioned, we've blown up the round complexity. But while we did blow up the round complexity, we kind of haven't messed with the communication complexity too much, because we've crucially relied on the fact that the number of that we're dealing with DPIR here, right? The number of locations that the server reads is sublinear in end, and so we're still sublinear in end in total communication complexity. And yeah, as I said, the server is purely passive. Okay, so that's step one. That's all it takes to do step one. And step two is another relatively simple step. But okay, first I'm going to define this notion of what I'll call a crypto oracle. It's kind of a silly name for an oracle that has this specific format. So it's the form of, like, it's B to the R. So it's B to the R in the sky. So it's like an oracle which itself has its own little private oracle that only it can touch, right? And so B is going to be a polytime, stateless, and deterministic Turing machine in the sky. And it has access to its own private random oracle, a truly random function that it has access to all itself. And so now the thing is, like, okay, suppose I could write OP as a crypto oracle itself. So like, suppose I can implement P with respect to a crypto oracle. Then I want to show that I can remove the oracle altogether from this computation and replace it with just a PRF. Well, so okay, so here again, this will be the result of the previous step. So we have this kind of passive server skdpr where, you know, the server never has to touch the oracle, but the preprocessing algorithm and the client both interact with the oracle. And that oracle, you know, whenever it does its response, has its own little private box. And we're going to compile that into a new version where we have a new version of prep and the client, where all they're going to do is going to run the original one and simulate and just run the algorithm B in its head. And anytime that B would access its own private random function, they're going to use a PRF. So just like some shared. And so the PRF key will be like folded into part of the key of the original scheme. And so because it's a secret key scheme, only prep and the client have access to this PRF key, right? So that's all it takes, yeah.
So P here stands for some, like, with nice property, like advanced primitive. And so like you mentioned that you haven't told us about nice properties they have. So like the property here will be, so like such kind of primitive P will be able to implement this crypto oracle.
Yeah, so it's, yeah, so what I mean, exactly, what I meant by nice and like that general property is exactly the property of all primitives that can be implemented with respect to a crypto oracle. Yeah. And so I haven't really justified to you, I haven't really justified to you at all, like, how big of a class that is, but I'll in the next slide, or maybe the next slide, I can't remember, I will do that. Okay, yeah, so, but now that I've given you that definition, exactly what I just said, and what this question was, yeah, so any primitive that exists with respect to a crypto oracle is exactly this thing that I hid from you before. So then we have this full statement of theorem one. And as I said, we'll kind of ignore theorem two for now and maybe get to it later. Well, we'll see if there's time. But first I want to kind of justify to you the strength of crypto oracles, like I said I would. And I want to justify it by saying, okay, I can implement virtual black box obfuscation with respect to a crypto oracle. So this is like one of these immensely powerful tools that are kind of too powerful. They can't even like exist in the plain model, but we can get it with respect to a crypto oracle. And the proof sketch is very simple. So I'm going to define a crypto oracle that is going to implement kind of the two algorithms that define obfuscation. There's an obfuscation algorithm and an eval algorithm. And all I'm going to do is on input, a circuit and some randomness, I will just use my random function to do an authenticated encryption of that circuit and send back the ciphertext. And then on input a ciphertext that encrypts the circuit and an input, I will just decrypt it, make sure that it's not bought, and then send back the evaluation of that circuit on that. And so this is this is like kind of an implementation of the interface of obfuscation with respect to this crypto oracle. And it's very easy to see just by the security of this authenticated encryption that this actually achieves the security notion of virtual black box obfuscation.
Why did you need authenticated encryption and not just encryption?
Yeah, so you need authenticated encryption because like you want to make sure that when someone does ask for an evaluation of another circuit, that it's not like some new like gobbledygook thing. Like they're not able to like mal some circuit that they got before and produce an obfuscation for a different circuit, right? That could allow you to break the security of obfuscation. And so we want to just make sure that you can't actually like get, you can't get evaluations of circuits that you haven't already asked for obfuscations of. Yeah.
So when you convert the SKDPR to passive server SKDPR, the number of rounds blowing up, it make the communication trivial. Say if the number of rounds is more than n.
Yeah, but remember the blow up in the number of rounds is only at most equal to the number of locations that are read in the original version, right? And since it's DPIR, this is crucially where we're using the fact that it's DPIR and not like a standard preprocessing PIR. That number is sublinear, and so it blows up. Well, it might blow up the total communication in general. It does not blow it up to being linear in the database size. It's still sublinear. But okay, so what I've shown to you is kind of that the crypto oracle is kind of very powerful in this sense. You can give virtual black box obfuscation. We have this other result that we mentioned in the paper that you can actually also kind of instantiate the generic multilinear map model. And so you can as well, so you can get OT, FHE, arbitrary, other things like that. So this really is like a very broad class of crypto primitives. Like I'm kind of hard pressed to come up with crypto primitives that aren't already implementable this way. Yeah.
So just to get a better sense, can you sort of sketch how you do the public encryption using a cryptography?
Yeah, so like what are the algorithms of public key encryption, right? A public key encryption scheme has like has a keygen, has enc, and has that, right? Right, and so all of these guys have access to their own like to a private random function. And like the private random function just like can kind of do all the work for you, right? Is really what is. And so so really just like the keygen is just going to output some specific tags like PK, SK. And where like because I have a random function, like enc can kind of check, or like def can kind of check this like the relationship between PK and SK, that like PK and SK are a matching pair, right? Like it could be the case that like PK is like as R of SK or something like that.
Okay.
Right. And so then for encryption, I'm just going to like output an authenticated, like I'm just gonna do the same thing. I'm gonna output an authenticated encryption of the message. Like with like the PK, right? And then DEC can just decrypt ciphertext using like the authenticated decryption. And then check if SK actually, okay, so here I probably want the opposite RFPK. Actually, no, either one works. Like it just needs to be checkable. Like check that R of SK is equal to the PK that I get from decryption, and that is not aught, like not aught. And then if I do those checks, right, and then I'll send back an answer. So it's relatively easy to see that this gives you a public key. Like, and so like the message here is like, it's really just that like you can kind of like, it's almost like you're living in a world where you have a trusted third party that can help you at all times, right? That only the honest parties get to touch, right? Which is an incredibly powerful thing in terms of cryptography, right? It's not quite that powerful because like the honest third party is only a random function, but still like you can do a lot with a random function is the thing.
The key is only the honest party can touch this random function.
Yeah.
The adversary cannot.
Yeah,
That's,
exactly.
the power.
Yes, exactly. Yeah, that's really, you get so much power from that. Anyway, so now that I've kind of shown you the actual like proof of theorem 1, I want to kind of give you like some corollaries about it. And so the first corollary is kind of just that like that we like, as you saw from this previous slide, like we capture a very broad range of primitives with the notion of a crypto oracle. And so
FHE can also be.
exactly, yeah.
How do you do the evaluation, the homomorphic evaluation?
I will just like because everything can happen with respect to some authenticated encryption that only we have and you don't have. I can just like my evaluation algorithm can just be decrypt and re-encrypt, like decrypt, eval, and re-encrypt.
But what if the server just calls evaluation but with different randomness?
Yeah, so that is something that is like you do have to be careful of, and so what you need is an authenticated encryption that like is still secure even with adversarially chosen randomness, which is something that you can relatively easily construct. But other than that, you're fine. Yeah, so it's relatively easy to see that like.
So the server must call the oracle to evaluation.
Exactly.
It can supply arbitrary random. So that's the model.
Yeah, exactly. Yeah.
This is what you mean by black box. The server cannot do homomorphic evaluation by itself without calling on.
Yes, that is exactly. Yeah, which you've okay, and so just to finish, you've preempted my next slide. So just to finish out this slide real quick. So what the corollaries that we kind of have is we have like, okay, so if there's a black box construction of SKDPR from, I can replace P with FHE, I can replace P with IO, I can replace P with FHE plus IO. I can do whatever I can do like so many things here. But one thing I do want to kind of just quickly draw your attention to before I go on to the next slide is that like the prior lemma can actually be very easily adapted, like the one from the previous slide, to give VBB for even oracle-aided circuits. Like I can't have it, like what I can't actually do is I can't do like self-referential circuits, but that's fine. Like oracles, like circuits that can call the same general oracle. But what I can do is I can even capture like kind of a large range of non-black box techniques, such as like evaluate crypto under obfuscation, or like run FHE, run an FH or like run signatures under FHE or something like that. I can even capture like that type of thing.
As long as the server calls an oracle.
Yes, as long as the server calls the oracle to do this. And
Call the oracle for both the crypto and the.
yes, exactly. Yeah. And then the second corollary I want to note is that like our compiler that we've been through kind of is pretty agnostic to the presence of other assumptions. And so, you know, like if I have a thing that says skdpure exists assuming making black box use of some crypto crypto primitive p plus assuming DDH, then I might as well have just constructed skdpure with just DDH. And but so here's kind of like here's kind of getting at what your point was, Elaine, that we crucially need the fact, like in this type of in order to construct something like new or different, like what we can rule out is like constructing in the generic group model, right? And so we like crucially need actual like concrete use of the fundamental algebraic structures of the whatever crypto assumption that we're making here. And so like what we're really getting at is that like if we define FHE like define FHE to mean that there is an eval algorithm out there, and black box use of the eval algorithm means that I call the oracle to evaluate, then that's what we capture here. What we don't capture, crucially, is a world where there is some like way to do encryption, and then the server can do evaluation only messing with bits on its own without touching the oracle, right? Like if it knows like concrete algebraic structures of the group that it's acting over or something like that, then that escapes our bound here. Yeah. Yeah, and I think this is kind of just saying the same thing again, which is so we have these prior positive results, which both, you know, you have this permuted codes of noise and based on the ring LWE assumption, and both of these kind of really fundamentally make concrete algebraic make use of the concrete algebraic structure of the underlying assumption. So like here in these first two results, they crucially use the fact that you have hardness over something that already has some locally decodable code structure to it. And so like the concrete thing that you're working over has some structure, and then you also get and you also are assuming hardness on the side. And similarly, like we have this kind of idea where we're using the concrete algebraic structure of ring LWE, of like the ring and ring LWE, to do some pre-processing over top of it. And we're making use of that concrete fact, and that pre-processing does not work in like some generic sense, right? It's crucially using concrete facts. And then our result kind of shows that this concreteness is there. Okay. I guess I'm pretty much out of time. And so I'll just close out and won't go delve too much into this theorem 2. And so just to summarize, we have our two main theorems, right? So we have this kind of large class, and we get these. If I could construct it from any primitive in this large class, I could construct it just from only functions, and I almost rule out, okay, no, I wouldn't say almost, but like I make progress towards ruling it out from just one-way functions. But of course, this leaves open some nice open questions, fully, like I would really like to just get rid of those two adjectives in theorem 2. And really like the fundamental adjective is the two-round adjective. I don't really care about passive server, it turns out. And second is like zooming out is like, we can kind of ask like, can we hope to give new constructions of DPIR in general, kind of using our idea of like the fact that we need to kind of focus on these kind of concrete algebraic properties of whatever assumptions we use. And ideally we would like something, really any new assumption would be interesting, but ideally we would like something that's maybe weaker than ring LWE, or at least more standard than permuted codes of noise.
It's like theorem 2, like this a meta reduction proof, or how do you prove theorem 2?
Yeah. So
is it like a generalization of this IR 1889?
No, it is not. What it is much closer to is if you're familiar with in CHR, there is a proof that you can't build information theoretically secure PIR, like preprocess SK PIR, with that is static and unbounded and stuff like this. And it's much more close to saying, I'm going to take that information theoretic results and kind of apply it here. Because, okay, so actually, let me go back a little while and point out one thing. Here, and when I did this removing oracles altogether step, I introduced the PRF here. But I didn't have to. Like, what I could get is a purely information theoretic object here, where instead of a PRF, I just have like a random oracle, or like, and it's different than a random oracle because it's not a random oracle that is accessible to all parties. Like the adversary doesn't get to touch it, right? So it's a secret random function that is shared by the honest parties. But this is a purely information theoretic object. And so what our result actually is doing is essentially it's just making some sort of information theoretic argument based on like adapting that proof from CHR. And like that proof from CHR is kind of like going along the lines of like these things of, oh, if you could, it's kind of this sort of win-win argument of either you can release the secret key or you can't, or like if you could release the secret key, you could compress the database. And if you can't release the secret key, then the secret key must be large. And it's both of these are like these kind of entropic information theoretic arguments. And so we're just adapting those arguments to the setting of having this exponentially long random secret key. Yeah. But yeah, so that completes the talk. Yeah.
Can you give a bit of intuition on why the 2 round comes in? Like why is it 2?
Yeah. So it's like really let's see. Okay, can I give you a very short version? The very short version would be, so as I was just kind of saying, we're kind of building on top of this previous result that ruled out information theoretic SKD pure. And what that previous result was saying that it kind of comes to the conclusion that in order for you to have a deep pure that is secure for an unbounded number of queries, your secret key needs to be very large. Okay? But what we had, and what I was just showing is like we kind of live in a world where it's an information theoretically secure SKD pure, but where the secret key is an exponentially large function. Right? And so our adaptation is about trying to handle the fact that we do have a very large secret key. And what we want is we want to kind of show that you can kind of use just only some small part of it is actually the relevant part. But crucially what that involves, like as a proof technique that we crucially use is that we can kind of like extract like the heavy set of the queries made to that random function. But if it was a multi-round scheme, the queries made to the random function now starts to depend on the database. And if the queries made to the function depends on the database, then I can't extract that out without extracting necessarily perhaps the entire database over time. Like if I run this many times, I can't make my sort of information theoretic arguments about compressing the database anymore. Yeah.
Can I elaborate more on like the second question? So like if you have new assumptions, or like what kind of property like are you looking for from that assumption such that it will like likely to imply deep PIR?
Yeah. It's not super clear to me. I've spent a good amount of time thinking about this, and I don't know if I have like a super great takeaway for it. What it crucially seems to require, right, is it requires like kind of some. I mean, like okay, maybe I should take a step. Like I don't think I even necessarily have like a very strong kind of intuitive explanation for these two constructions that kind of unifies them into one kind of general technique, right? They have similar-ish flavors, but they kind of diverge in many ways, because like this kind of the ring LWE construction really is based on kind of I'll build a normal PIR and then I'll pre-process the server. Like I'll do some sort of like algorithmic technique on crucially using, you know, my algebraic structure here, and I'll pre-process the server's runtime. And on the other hand, this kind of permuted codes with noise assumption is more along the lines of like, oh, I'm going to start with something that I know has this kind of nice query structure to it, and then kind of mess with it enough to get security. And so these have like similar-ish flavors. But it's not like a priori super clear, it's not particularly clear to me, I guess, overall, like even exactly what I should be on the lookout for. Yeah. But, you know, like one natural question is like basically everything that we know how to do from ring LWE, we know how to do from LWE. So a natural question is like, can I do it from LWE? And when I focus in on that more natural question, like then it kind of I go down the line of like where does the ring LWE construction fail? And it kind of fails in like in the fact of like the preprocessing technique I know of only works for this algebraic structure and not that one. Right. And I don't know how to get around that.
You found the construction of the somewhat encryption. Like some other construction were arithmetic, some were.
Yeah, actually, okay, so yeah, I kind of swept that under the rug. We there are these constructions of somewhat homomorphic encryption based on
Opposing GCP.
yeah, yes, and that does actually work with our technique. You do get
It was also before by binomial decentralized. Opposing GCP. It's like a GCP but with some noise.
yeah, like
It's overfilled.
yeah, it's like it's kind of you would like kind of think of it as being like kind of a one-dimensional analog of like LWE or ring LWE in some sense. And so you end up with like the natural structure that you have to work with is everything is you're doing operations just directly over a field. And so the pre-processing for this scheme works directly well with that. Yeah, we just so that does work. I just, you know, we as a community we care about less about that assumption than ring LWE is the only reason I haven't said it. Yeah.
And where those multi-linear mapping work on this construction. Multi-layer. Like by multi-linear mapping.
Sorry, like what are you?
Like multi-linear mapping.
Yeah. Ooh, like does that also give you DPR is the question, you mean?
We don't have instantiation.
Yeah,
Structure.
yeah, exactly. So it's so generically it shouldn't. Like we actually this work shows that generically it shouldn't work, and we don't have instantiations that we believe to be concretely secure. Yeah.
Like something like any like specific algebraic structure that cannot be like used to.
No, I don't know.
You need those like candidate schemes, is that what you mean? Like there are some candidate schemes, but think that there have been some attacks as well.
Yes. There are some like layered randomized encoding, something like it's called multi-layer mapping, layered multi-layer mapping. They have some construction based on like some of them based on WE, and some other based on some like algebra. I remember there were two classes for candidates, but both are like attacked and fixed for a couple of times. So not very.
So that is called multi-linear map.
They I think they are called layered, multi-layered, layered randomized encoding.
Yeah, it's interesting to look at these.
let's thank the speaker.